All right, 2008 number 4. We have a nice velocity particle motion question, so this should be a good one. Part A, we have find the time, the time and position of the particle when the particle is furthest to the left. Well, I can tell from my graph, remember this is my velocity graph, that my particle starts someplace. It starts at -2, that was given to us in the paragraph. And since velocity is negative because it's below the x-axis, that means that my particle is going left until t equals 3, and then it's going right until t equals 5, and then it moves left again. That's all based on velocity being negative, positive, and negative. So what I need to look at is, there's a couple different ways to do this question, but I want to look at where's my particle starting, and then where is it at t equals 3, because that's when it moves left. But then it moves left again until t equals 6. So I want to look at a couple different scenarios here. One thing you could do is a snake diagram. You don't have to, it didn't ask for that, but it's definitely a possibility. So for part A, what I'm going to do is I'm going to look at what is the position at 0. And I know that it's at -2. And then I want to look at what is the position at 3. And I know if I want to find the position of the particle after 3, I think we're talking minutes here, I'm going to look at the initial position plus how far did it move from 0 to 3. Let's see. And so that's going to be -2, let's see here, -8, because that is the area under the curve for velocity from 0 to 3. So that means at -10. So the position after 3 minutes, I got to check my units on this, is -10. The position at 0 is -2, and then I want to check the position at 6, which is -2 plus my integral from 0 to 6 of v of t. So that's going to be -2, and then I have -8, because that's the area below. From 3 to 5, the area underneath is a +3 because it's above the x-axis. And then I have -2 again, so that's going to give me a total of -9. So the position at 6 is -9. So those are my different positions. So when is it furthest to the left? After 3. Farthest left at t equals 3. And the position at that time is -10. So that's your final answer. It wants the time and the position of the particle. So that's part A. Part B. Let's see, for how many values of t where t is between 0 and 6 is the particle at -8? Explain your reasoning. Well, if I look at this, knowing everything that I have here, I already know that the position at 0 is -2. I also know that the position at 3 is -10. The position at 5, this I can easily figure out. Looking at my graph, I can say that this area underneath is 8. This is 3. So the position at 5 would be -2 minus 8, which is -10, plus 3. That's -7. So that's exactly how I got all these answers in part A, just looking at the area under the curve, which was given to us. And then I also know that the position after 6, t equals 6, is -9. So as I can see, it's got to be, I have to hit a position of -8 someplace in here, again in here, and then again in here. Each one of those intervals, 0 to 3, 3 to 5, and 5 to 6, I have to hit -8 in there each time. Now here's the big thing. When I'm trying to guarantee that I'm hitting something, this does not have to do with derivatives here. I need to know a theorem, something that's going to prove this will happen. So what I can say is that because, let's see, I have a differentiable function. If it's differentiable, then it has to be continuous. Since x of t is differentiable, it is continuous. So I have to get that stated in there because none of these theorems work without continuity. IVT guarantees that x of t will equal -8 on each interval from 0 to 3, 3 to 5, and 5 to 6, and therefore x of t will equal -8 at least 3 times. Once on each interval. Okay? So again, IVT is a theorem that states if I have a continuous function and my y values, in this case going from -2 to -10, I'm guaranteed to hit every y value in that in between. So I'm going to hit -3, -4, -5. It's guaranteed to happen. That same idea is happening on this interval when my particle is going from -10 to -7, and once again from -7 to -9. Okay. Part C. On the interval 2 to 3, is the speed increasing or decreasing? Let's see. The speed is, and we have to figure out, is it increasing or decreasing? If I look at my graph here, from 2 to 3, I'm looking right this part of the graph right here. I can say that at that part of the graph, the velocity is negative because it's below the x-axis, and acceleration, which is the derivative of this graph, is positive because at that part of my graph, I have a positive slope. It's increasing. So what I can say is that the speed of the particle is decreasing since v of t is less than 0, negative, because it's below the x-axis, and acceleration is greater than 0, it's positive because my function is increasing. The derivative at that time, 2 to 3, is increasing. Or I'm sorry, the derivative at that time is positive. Part D, finally, during what time intervals, if any, is the acceleration negative? Let's see. Acceleration is less than 0. Well, that means that v prime has to be less than 0. And when is that happening? That's just when velocity is decreasing. So I want to look at my graph and I want to find out when is velocity decreasing. So looking at my graph here, I can see that velocity is decreasing from 0 to 1, and then it's decreasing again from 4 to 6. So those are the intervals that I want to put down. So I have from 0 to 1, and then from 4 to 6. And there you go. These are my explanations right there. Final answer, and you are all set on that. Either way that you write out your intervals is fine.